sampling distribution, and I asked you to take a look at number 35, and I said you could not do it. James, why couldn't you do that? Okay, yeah. Okay, we got a new rule. We got a new rule. Every day between 1:15 and 2:15. Nobody's allowed to say the word it. You are not allowed to say the word it's. Especially we don't put the word it's in our homework assignment. Now here's why. Okay, when you say it's normal, I don't know what you're talking about. Are you talking about the population distribution? Are you talking about your sample was normal? Or are you talking about the sampling distribution? Okay, so I need you guys to be very specific. That's why we wrote that assumption out so big. Okay, so I need you to be very specific. So when you said it's normal, you meant to say what did you mean to say?
Population distribution
isn't normal. And remember what we learned yesterday. We learned that if the population distribution was normal, in other words, all of those numbers in the bucket, if we drew a picture of them and they came out to be a normal distribution, no skewedness, no outliers, which I don't think ours would have been, right? But if the population distribution, all of the original numbers were in fact normal, then the sampling distribution will also be normal. That's what we learned yesterday. So what I hear you saying is that in this problem, the population distribution was not normal. In fact, it was skewed right, I think they said in that problem. So we're stuck. What's the sampling distribution going to look like? All right, you're about to be exposed to by far the most important theorem in all of statistics. We talked about a magic number in this class before. You've heard that magic number before. Today you learn why. Except it's not really 30. But and it's called the central limit theorem. What the central limit theorem says is this: if you take a large enough sample size, it doesn't matter what your population distribution looked like, your sampling distribution will be normal. What does that mean? I mean, let's think about this for a second. What is a normal distribution? A normal distribution, 68% of all of these guys will be within 1 standard deviation of the mean. 95% will be within 2 standard deviations of the mean. It won't have any outliers. We now know that all these x bars will be pretty close to the mean. In fact, we can figure out what percentage of the x bars, where they're going to be. Ultimately, that's how they get the bottom part. They say, hey, you know what? Here's my guess. But I know I can't be more off than plus or minus. They can get that from the tables. Okay? That's how they're able to know how far apart they probably are from the mean, from the actual real value. Okay, so let's take a look at this now. I guess the good question here is, well, how large is large? How big of a sample size do I need to take? All right, pretty good illustration in your book. Go to 522. The graph on the top left, that's our population distribution. That's red. That's the big bucket of numbers. Kind of looks like your test scores. A whole lot of zeros and then a few way out there. Now, nobody's going to confuse that distribution for a normal distribution, right? That's crazy skewed right. But take a look. If you just take a sample size of 2, it's the one right next to it on the right. Those are all the x bars you're going to get if you just take a sample size of 2. Now, how in the world does that work? Let's think about this for a second. So I'm back here. And so I'm getting every possible sample size I can get of 2, and I'm getting the x bars. Well, we got these crazy high ones, but what's going to happen to the crazy high one when it mixes in with all these other ones? when I have 19 and 11 together? Aren't they going to come down? I'm not going to have those really big ones anymore. That's what's happening with that sample size of 2. Now, does a sample size of 2, did it normalize it? Was the sampling distribution normalized? No. Look at that, still pretty skewed right? These big ones still, I mean, it mixed with a couple of other 19s and still had some big ones out there. But look what happens when we just go to a sample size of 10. So if I grab 10 of these guys and I find the mean of them, well, now that 19's mixing with a lot of these other ones. Still a little right skewed, but looking much more normal. How about if I take 25 of them? That's what you guys did. You took a whole bunch of these, and you all did it, right? You calculated the mean. Didn't those big ones, you know, get mixed with the other ones, and when you got your mean, it was more in the middle? And that's exactly what's happening there with that sample size of 25. All these x bars is kind of what we've got here. These are sample sizes of 20. Okay, if we graph this, okay, even though I think the population distribution is a bit skewed right, if we graph this now and maybe put some more of these on here that we've got, we would have a pretty normal shape of the sampling distribution. Now we might still be a little skewed right. Okay, maybe 20 wasn't quite enough, but we're getting there. So to answer the question, how large of a sample do you need to take so that you know your sampling distribution is going to be normal? It depends. It's a really bad answer, but it depends. If your population distribution was just a little bit skewed, I mean, that thing's crazy skewed, that population distribution we have in the book. But if the population distribution was a little bit skewed, it wouldn't take as big of a sample size to normalize the sampling distribution. But let's say you don't have any idea what the population distribution looks like we don't know here. Probably skewed right, but we don't know. What is a safe number? And that's where that number 30 comes from. If you go into a problem and take a sample size of at least 30, you can be pretty confident that your sampling distribution is going to be normal. Our book takes it to the next level in the next chapter. It's saying, okay, you want to be really sure your sampling distribution is normal? Take at least 40. So if your sample size is at least 40, then you know your sample mean, your one sample mean, is swimming in a world that is normally distributed. We ain't going to have any of those in there. We're not going to have any outliers. Okay, what? Question?
Oh, no, you can answer.
Okay. Okay, so now we have, yeah.
So why don't they just take a poll of 30 or...
You guys just did 20 and you whined like a bunch of little kids. Oh, this is so hard and whatever. But what if it's cancer patients of this certain type? Maybe there's not that many that even would want to be a part of it or that you can get. You know what I'm saying? So sometimes it's hard to find a really big sample size. Sometimes it's easy. I'm trying to figure out who's going to vote for the next election. That's not so hard. But sometimes it's tough to get that many and do a full experiment on all of them where they have to be committed for a long time. So your goal is the more the merrier, right? The bigger our sample size, we know the more of these are going to get close to the right answer. But sometimes it's not as easy as that. Okay. All right, so we've now added to this assumption now. We have two options going now. You're going to have both these types of problems tonight. If they tell you that the population distribution is normal, just go with what we had before. I know if the population distribution is normal, the sampling distribution is going to be normal. But if they don't tell you anything about the population distribution, or like in 35, they tell you that the population distribution is definitely not normal, then this is going to be our justification as long as we had a big enough sample size. So you're going to write yes. Since our sample size is greater than or equal to 40, that's the number that we're going to be testing out here. And I think in the first problem is in your sample size 50 or something like that, you actually write in what your sample size is. By the central limit theorem, then the sampling distribution will be normal. If I have a large enough sample size, all of my x bars will be normal because of the central limit theorem. Do I see the word "it's" anywhere in here? No, you don't. Do I see just the word "stated" anywhere in here? You stated people. What is stated? There's 3 distributions. What was stated? You gotta tell me.
But we can write stated for the simple random sample, like you have on the board.
Correct, because they just said simple random sample. Although I'll tell you what, tonight, take a look at that. Tell me if you think they're good simple random samples. And some of the problems tonight, take a look at them. And we keep doing the problem, we just say up here. Okay?